Alright, let's talk about dihedral groups. So we're going to let G be a group of, well, I guess not dihedral groups. Groups which are either dihedral or cyclic. So anyways, we have a group of order 2p where p is a prime which is not 2. And we want to prove that either G is cyclic or dihedral. And usually this would be D2P. There's different conventions here. Some people, to say the dihedral group of... So the thing is, if you look at a dihedral group is a group of symmetries of, say, an n-gon. And if you're referring to the group of symmetries of an n-gon, then that group is going to have 2 times n elements. And so sometimes what people will do is they'll refer to the dihedral group of symmetries of, say, a p-gon, they'll call it dp, where p denotes the number of number of vertices on this polygon. But some people will refer to it as 2 times p to refer to the number of elements in the group. So I think I see this one a little more often, but the professor that I'm currently taking the course from prefers this notation, and that's fine. So just so you know, that we're going to be using this one throughout this exercise. So the dihedral group dp is the dihedral group of symmetries of a regular p-gon, and it will have order 2p. Okay, so let's get started. We know that by the CELO theorems, the number of CELO p subgroups divides 2 and is equivalent to 1 mod p. And so, because we're assuming that p is a prime which is not 2, we know that if you start at 1 and then go to the next thing of the form 1 mod p, the next thing you're going to get to is p plus 1, which is already larger than 2. And we know that for np to divide 2, it's got to be either 1 or 2. And so therefore it has to be 1. So there is only one unique CELO p subgroup, and we'll call it p. And we know that all CELO p subgroups are conjugate in G, and therefore this is a normal subgroup of G. Again, this is one of the most useful facts from the CELO theorems. So anyways, since this is a CELO p subgroup, it has order, well, if the group has order 2p, then it must have order p, and the only group of order p, since p is prime, is z mod pz. And so p is isomorphic to z mod pz, and so p must contain some element g which has order p and which generates p. So p is generated by this element g which has order p. Okay, and then we know that 2 also divides G, and so G must contain an element of order 2. So we have an element of order 2 and an element of order P, and we're going to prove that G is the group generated by G and H. So this is all words that you can make using the letters G and H. Okay, so how do we prove this? We're going to observe that if you look at this thing, the collection of things of the form G times H, this is just G raised to some power and this is H raised to some power. This is going to be a group since it's going to be a subgroup of G since this is a normal subgroup of G because it's a CELO p subgroup, and we prove that we prove that all the way up here. Okay, so we have this normality here, and one of the isomorphism theorems tells us that if you take a normal subgroup and multiply by just any subgroup, then you're going to get a subgroup. Okay, we also have that, well, if you take anything like G to some power times H to some power, then this is going to be, anything here is going to be a word involving the letters G and H, and certainly this is a subgroup of G. Okay, so we have these inclusions, Now we have a typo, and now to estimate the number of elements in this group, let's suppose that we have two elements in the group, say GN1HM1 and GN2HM2, and we're going to assume that these two elements are equal. And note that these are what any element in this group G times H can be written in this form, because that's what elements look like. Anyways, okay, and we're going to say 0 between p minus 1 and 0 between 1, or yeah, you got the n's and the m's in those intervals because G has order p and H has order 2. Alright, so first I claim that n1 is equal to n2. Well, I claim that n1 is n2 and m1 is m2. So if you have two elements that are equal, then the g powers are the same and then the h powers are the same, and we can use that to estimate the number of elements in here. So anyways, so let's assume for contradiction that m1 is not m2, which, I mean, contradiction proof's not the best, but whatever, it works here. So without loss of generality, suppose, if they're not equal, one's going to be 1 and the other will be 0. Here I wrote 2, which of course is the same as 0 because it, in the sense that h to the 0 is equal to h to the 2 is equal to the identity, since h is order 2, but that doesn't matter. Because I said 0 between m2 is between 1 here, I should change this to 0 to be technically correct, which is the best kind of correct. So if we say m1 is 1 and m2 is 0, then what does that tell us? We have gn1h is equal to gn2, and so we multiply on the left by g to the minus n1, and we commute the exponents here, which we can do because we can commute exponents. And so h is equal to g to this power. So h has order 2, and g to this power is going to be contained in the subgroup generated by g. Okay? And so h cannot have order 2 because this element cannot have order 2 because it's contained in the group generated by G, which is a group of order P. And any element of the subgroup generated by a group of order P must divide must divide P. And so it's either going to be 1 or it's going to be P. So either this thing, which is equal to H, either its order is 1 or its order is P. In both cases, these things are both not 2. And so we have a contradiction, and thus N1 must be N2. And then from there it's easy because then that says you cancel and you get G to the N1 is G to the N2, and so N1 equals N2. Okay? And so therefore, the number of elements in here must be, is this actually an equal? If you've got two things, if two things in here, right, so if you've got two elements in here that are equal, then the indices must be equal, and so we've got P times 2 choices, and that's just G times H, and so we're good. Okay, so then we estimate since we have this containment up here, G times H is contained in the group generated by G and H. The order of this group is greater than or equal to the order of this product, which we know is equal to this, which is 2P, which is the order of G. But the group generated by G and H is a subgroup of G, and if it's a subgroup of G which has the same order of G, then it must be precisely G. Okay, so we have this nice form for G. It is a group generated by these two elements, and now we can proceed from here. Alright, so we know that P is normal in G, and so if you take the generator G of P and you conjugate it by H, then you're going to land back in P, which is the group generated by G. And so for this to be contained in the group generated by G, it must equal G to the n for some power of G. And since G has order P, n is between 0 and P minus 1. And then we have this equation here, and this is just a whole bunch of things with the symbols that just magically work out nice, and I'm not quite sure how you would come up with this on your own, but I mean, it works. So yeah, some of the stuff in these next steps are it seems a little like black magic to me. I don't know how you would come up with these, and it doesn't like help me understand what's going on with these groups better. It's just clever manipulations of symbols, which is the kind of stuff in algebra that I don't really care for. But it's just a personal preference, and it allows us to prove this problem, so let's do it. You take g to the n squared, that's g to the n to the n, then you replace this g to the n with hg h inverse, but now if you line all of these up in a row, then you're going to get hg h inverse, hg h inverse, hg h inverse, and you're going to get all these terms, all of these h inverses, which will appear between the g's, and so those will all cancel out, and so all you'll be left with is the h on the left end, and then all the g's in a row, all n of them, and then this h inverse on the right. But now we know that substituting this thing again, we get hg h inverse because we're just replacing g to the n with hg h inverse, this thing right here. And then you cancel the h's since h has order 2, and you just get g. So g to the n squared is equal to g, so multiplying on the right by g inverse, we get g to the n squared minus 1 equals 1. And since g is in P, the order of g must be P. Rather, since the group generated by g is equal to P. Because just because you have an element of P, it could have order 0. But here g is special because it's the generator of P. So anyways, because this is P, the order of g is the order of P, which is P. And so in order for this to be true, P must divide n squared minus 1. And you can write n squared minus 1 as n plus 1 times n minus 1 over here. So in order for this to hold, either P is going to divide n plus 1 or P is going to divide n minus 1. So let's consider these cases and see what happens. If P divides n plus 1, then I don't know why I use these j's here. I think this is another thing where, like, because these formulas were so tricky, I had no idea where to go, and so I think I just looked up online for some hints. And luckily, like, this is a fairly standard problem. It's been done before. But again, I don't quite know how you would come up with this on your own. I'm starting to realize that with some of these algebra problems, the trick to solving the problem is to have seen it before, so that you know what trick to use, which is not a very good way to do math, because you should be able to come up with everything on your own even if you haven't seen anything before. But yeah, I don't know. Some problems like this I just don't know. But anyways, so we have n plus 1 is mp, so there's some integer multiple of p will give us n plus 1, and so then we just do some calculations. HGH inverse is, well, this is g to the n, and then that's g to the n plus 1 g to the minus 1, because that's just exponents, but we can replace n plus 1 with mp, but g to the mp is, this is g to the p is 1, so you could think of this as g to the p, that whole thing to the power of m, which is just 1 to the power of m, which is 1. Anyway, however you want to think about it, this cancels out and we just get g inverse. So hgh inverse equals g inverse. And so g is the group generated by g and h, and they satisfy g to the p is equal to the identity e. And that's because, well, right, because G has order P, and then we know already H has order 2, but then we have this equation, or this relation HGH inverse equals G inverse. And if you know anything about how we typically define the dihedral group, this is precisely the dihedral group on symmetries of regular P-gon. Okay, so in this scenario we have G is D is the dihedral group. So alternatively, we're going to suppose that P divides n minus 1, because that was the other scenario that we had here, and we'd better come up with G is cyclic in this case, and we'll show that that's true. Okay, again, I use J here, this should be n, so n minus 1 is MP for some integer, and then we basically do a similar thing here, G, or HGH inverse, we know this is G to the n, which is G to the n minus 1G, then we get this G to the MPG, so this is G, and so you multiply on the right by H, and you get HG equals GH. Okay, and so now let's look at this. This should start making you think about semi-direct products, because we know that G is equal to G times H. Well, not... What's really going on here is, so G is equal to the group generated by G and H, and by commutativity, this is going to be equal to G times H. Because if you have any word created by using the letters G and H, then you can just move all the G's together and all the H's together, and so these obviously are going to be the same. Let's scroll down. Okay, and so here, of course, we have H is a subgroup of G, and G is normal in G. And now if we look at the intersection of these groups, the intersection is a subgroup. The intersection of these two groups is both a subgroup of G and a subgroup of H. And so it's the order of the intersection must divide the order of the subgroup generated by G and the order of the subgroup generated by H. So it must divide the greatest common divisor of the two, which is the greatest common divisor of P and 2, which, since P is prime and not 2, is equal to 1. So therefore, the intersection of G and H is trivial. So if you have G is equal to product of two groups and the intersection of these two groups is trivial, then G is a semi-direct product of these two groups. And furthermore, since elements in these two groups commute, or since HG equals GH, we know that all elements commute, and therefore we can write G as a direct product of these two groups. But if we do that, then G is equal to the group generated by G direct product with the group generated by H, which is C norm of G. So that's just CP direct product with C2. And since the greatest common divisor of P and 2 is 1, CP direct product with C2 is equal to C2P. Here, of course, Cn is the cyclic group of order n. And so in this scenario, we have that G is cyclic. And so in the one scenario we had G is dihedral, the other scenario we had G is cyclic, and that's exactly what we were trying to prove. And so there we go. This is it. This is what we wanted to prove.